Okay, now with SN2 under our belt, let's take a look at SN1. SN1 stands for unimolecular nucleophilic substitution. So the 1 in the mechanistic label means unimolecular, which means that there is one chemical species involved at the rate-limiting step. Okay, so let's look at what's happening in this example here. So we have tert-butyl bromide, which is a tertiary substrate. So we know that this has some steric hindrance associated with it. The bromine, as we've seen in many examples now, is a good leaving group. And then over the arrow, we have water. So what do we know about water? Well, we know it's a weak acid, we know it's a weak base, and we know that it's a weak nucleophile. We also know that it's a polar protic solvent. So we know all of these things about water. And so when these chemicals are combined, what happens is that you get tert-butyl alcohol as a product along with a bromide ion and H3O+, or another way of saying this would just be HBr aqueous. Okay, so we do have a substitution that's occurred. However, because we started with a tertiary substrate and a very weak nucleophile, those two are unlikely to react with each other through an SN2 pathway. Therefore, there has to be another mechanism. Another mechanism is the SN1 mechanism. Now, this is an example of what's called a solvolysis. In a solvolysis, the solvent acts as the nucleophile in the reaction, so it's participating in the reaction. So let's draw a mechanism for what happens. Now, you might recall that we've actually already drawn this mechanism. This was the example that we used when we looked at the overview of substitution and elimination reactions at the very beginning of the packet. But let's draw it again. So in the first step of the mechanism, this compound ionizes. So you get a carbocation and a bromide ion. And you also have water in there. Water is a weak nucleophile, but a carbocation is very strongly electrophilic. So that compensates for the fact that the water is a weak nucleophile and allows the attack to take place. The rest of the mechanism is exactly like what you've seen in the acid-catalyzed addition of water to an alkene. So you get an intermediate that looks like this, and then another water molecule acts as a Bronsted base and removes a proton from it to give you tert-butyl alcohol as the product. So in the SN1 reaction, carbocation formation is rate limiting. So that's going to be our slow step. And another thing that we can mention here, not just in SN1 reactions, but pretty much any reaction, proton transfers. Proton transfers are usually fast steps. In fact, proton transfers are going to be the fastest steps that you'll see in mechanisms between two compounds. The rate law for an SN1 reaction, remember that the rate depends, because it's a unimolecular reaction, on the concentration of one chemical species. So for an SN1 and for an E1 reaction, the rate is equal to the rate constant K times the concentration of the substrate, because everything hinges on that ionization step. We're just waiting around for that to happen. So let's also make a note that this is the same rate law for E1. So knowing that the rate limiting step is carbocation formation informs our understanding of what types of substrates are going to be able to react through SN1 pathways, or the SN1 pathway, I should say. So that's going to be anything that can form a reasonably stable carbocation. So that includes secondary and tertiary cations that we would term aliphatic. So these are both aliphatic, meaning that they're not allylic or benzylic. Okay, so aliphatic is just alkyl group plus leaving group. That would be an aliphatic example. So when these ionize, you form tertiary and secondary carbocations respectively. In the case of a secondary cation, to get that to ionize, you will need to heat this. Any kind of allylic or benzylic substrate, that is to say where the leaving group is attached to an allylic or a benzylic carbon, will work in an SN1 reaction. Now, primary and secondary allylic and benzylic substrates may also react under SN2 conditions as well. But we're just looking now for what can form stable carbocations that could react in an SN1 pathway. The thing that will never react in an SN1 pathway, or the things I should say, are primary aliphatic or methyl substrates. So that would be things like this. That would be an example of a primary aliphatic substrate. Or a methyl substrate would be something maybe like methyl iodide. So those will never react in SN1 pathway. These do SN2 instead. Okay, the primary example of an SN1 reaction that you're going to see is a sulfolysis reaction. So let's look at some examples of sulfolysis reactions, work through some mechanisms, and start to incorporate carbocation rearrangements into these mechanisms. Because since the primary intermediate, or the most important intermediate in an SN1 reaction, is a carbocation, the potential for rearrangements exists. All right, so let's take a look at what we have here. We have a secondary substrate, and we can get even more detailed about this. The leaving group is attached to a benzylic carbon. So this is secondary and benzylic. The leaving group, as we already know, is a good one. So we have a good leaving group. And then over the arrow, we've got methanol. Now, what are all the things you know about methanol? You know it's a weak acid. You know it's a weak base. You know it's a weak nucleophile. And you also know that it's a polar protic solvent. The fact that it's a weak nucleophile diminishes the SN2 pathway. So it's not going to be likely to just attack on its own. It could, but that's going to be less likely than other faster pathways. So what happens here, in an SN1 sense, is that the compound ionizes. And that gives you a secondary cation that's stabilized by resonance. So it's secondary and benzylic. This is a solvolysis reaction. So the solvent acts as the nucleophile. The solvent is methanol. And so the methanol attacks the carbon with the positive charge. That provides this intermediate. This intermediate is then deprotonated by another solvent molecule, acting as a Bronsted base, and that's going to give you the product. Which in this case is an ether. Let's work through another one. We have a secondary substrate. We have a leaving group that's perfectly fine. And then over the arrow, water. And again, let's think about everything that we know. We know that water is a weak acid, it's a weak base, and it's a weak nucleophile. The fact that it's only weakly nucleophilic is probably going to suppress the SN2 pathway. We also know that water is a polar protic solvent. Hopefully you're seeing a pattern here because all the examples of SN1 that we've done so far have been in polar protic solvents. Notice that we're heating this as well. The heating is because this is a secondary substrate. So the heating is going to help ionize the substrate. It's going to supply the energy required to break that bond. So what happens then in the first step is the ionization. Which gets us this. This is a secondary cation. Remember, when we have a secondary cation, in particular, we want to be kind of suspicious. So what can happen here, I'm going to move this out of the way. What can happen here then is that something will move over from the beta position if we can get a more stable cation. Now in this case, we can. If a hydride shift occurs, that's going to give us a tertiary cation. So now we have a more stable tertiary cation. And now the water will attack. And the rest of the mechanism is identical to what you've seen before in acid-catalyzed addition of water to an alkene. Water attacks, that generates this intermediate, which is then deprotonated by another water molecule to give you an alcohol as a product. So the moral of the story for this example is to remind you that carbocations can rearrange. So you have to be on the lookout for that when you're drawing mechanisms and predicting products, not only for SN1 reactions, but for E1 reactions as well. Let's do one more example. So let's say that we have tert-butyl alcohol and HBr. All right, so what do we have going on here? We have a tertiary substrate, but unfortunately, OH is a very poor leaving group. Okay, so that's what we can say about that substrate. Now let's look at what's around the arrow. HBr, we know one thing only about it. It is a strong acid. And so in the presence of a strong acid, you should always think that something is going to get protonated. And the thing that's likely to get protonated is going to be something that's a weak base. If you had a strong base in there, then the strong acid and the strong base would have neutralized each other long before you arrived on the scene. So when you identify a strong acid in your reaction conditions, you should immediately look for a weak base, because probably the first step is going to be the proton transfer. And so the weak base that you have here, you have an alcohol. And you know that an alcohol is weakly basic. So the alcohol is going to accept a proton from HBr. So you've seen intermediates like this one before, many times. And at this juncture, what you might imagine could happen is that this gets deprotonated. And it's true that that's happening, but that's going to take us back to the starting material. If we're thinking in terms of a substitution reaction and that happening, then what is going to happen instead is the other possibility for intermediates of this type. And that is that water can leave. So water as a leaving group, or as a neutral molecule, is an excellent leaving group. So the water leaves. Remember, you still have a bromide ion in there that was released in the first step when the alcohol attacked HBr. The bromide ion can attack the carbocation and give you the product of a substitution. Now, for all of these examples that we looked at, these are all SN1 examples. But keep in mind that anytime you have SN1 happening, E1 is also going on. We just didn't draw the E1 products because we're focusing on SN1 for the moment. We'll look at E1 and the mechanism of that a little bit later in the packet.